So I think this is my first time following another presenter named Eli. Screen share. Oh, can you do that, Randy? So I'm going to be talking about a remote sensing based evaluation of the 2021 and 2022 curtailments. And my slides are coming up soon. I wanted to start by thanking the Klamath Tribal Water Quality Consortium that funded this analysis. Also wanted to note that this is analysis is still in progress. Literally nobody else besides me has seen this. So the good news is you get really current information that I've just generated in the last few weeks. The bad news is nobody else has reviewed it. So I'm sure that I've messed up a few things, and hopefully some of you can correct some things here. Let's see, can I move that a little bit? Yeah. Oh, there we go. Okay, that's better. Great. Okay. Yep. Okay. So 2021, the curtailments started pretty late. Irrigation season was pretty much over by that point. There were a few ranches on the Scott River downstream of Fort Jones that were paid not to pump groundwater for a few months. I haven't really looked at 2021 too much. I'm going to be focusing more on 2020 to 21 comparisons. So in 2022, surface water irrigation was curtailed in both the Shasta and Scott. In the Scott River, there were a lot of these local cooperative solutions that were developed by the landowners there, and those were intended to. They were focused almost exclusively on groundwater, with a few exceptions, and almost exclusively in the Scott, not the Shasta. They were intended to reduce water use by 30% for 2022 compared to a baseline year, usually 2020. Interesting, the term, I've read through these not real carefully, but I could not find a definition of what water use meant. And it's actually a trickier question than you would think that it is. So anyway, a 30% reduction in water use through a combination of practices that were specified by each ranch. So things like upgrading the efficiency of the irrigation systems, switching crops from, say, alfalfa to grain, maybe not watering the corner of center pivot fields or fallowing some whole fields, stopping irrigation early to reduce the number of cuttings in alfalfa, so there's less overall irrigation. Every ranch was visited periodically, or everyone who signed up, visited periodically by the RCD or CDFW with 24 hours notice to go out and to do whatever verification is possible on the ground there. And the water board, state board said about 90% of the groundwater irrigated acres in the Scott were enrolled in that program. So I'm going to talk about what remote sensing can show us about what the effects of this were. And I really love looking at these satellite images. I'm kind of a dork, but I think it's just really beautiful to look at the world from this different angle that we can't see with our normal eyes, from a different elevation, and also like hyperspectral sensors and things that we can't see. What I'm presenting today is primarily derived from these three different websites. There's OpenET, the Climate Engine, and the Sentinel-Hub EO Browser. At the Salmonid Restoration Federation conference a few weeks ago, some colleagues and I led a whole day-long workshop on remote sensing tools, including a pretty heavy focus on these three. And we've posted all the tutorials and information on my website here, so you can, anyone who wants to can take a look at that. I think this presentation will be posted later with all the links and things on the KBMP website. So about every 1 to 3 years, the US Department of Agriculture has aerial overflights of pretty much the entire nation at this really high meter resolution. So you can really see like the center pivots there, and you can get really good picture of that, but it's only every few years, right? There's satellite data from the European Space Agency. The Sentinel-2 flies over about every 5 days at a 10-meter resolution. So you can see it looks a little fuzzier, but you can see much of the same stuff. NASA and USGS have the Landsat satellites. It's multiple satellites. Average return time is around 8 days, and that's at a 30-meter resolution. So you can still see the same kind of features, but everything's getting a little fuzzier, right? I'm going to focus mostly on data from the Landsat, but some Sentinel data as well. So we've been looking at true color so far. That's just sort of similar to what your eye would see. These satellites have all different kinds of wavelengths and bands and sensors, and so from those you can look at ratios between different bands and different summaries and get things like these spectral indices of greenness. So two of them are NDVI and EVI. Don't really know what they are, but they're just different ways of measuring greenness. I really like this EVI one on the left there because it really you can really see the nice irrigated fields there, and they're differentiated from non-irrigated stuff and also from the forests. This is the Scott River near Fort Jones. Should have said that. The really cool thing about Landsat is it has a thermal sensor that senses the temperature of the surfaces of the Earth and the plants that are on it. It's not the air temperature; it's the temperature of the surface. And so, just as if we were to splash ourselves with water and then go outside on a windy, hot day, when the water evaporates off your face, you feel cool, and it literally is cooling you down. It's the same thing when a plant is transpiring water. When there's water leaving the plant and going up into the atmosphere, it cools down the plant. So you can see those blue circles there are the center pivot irrigation there, and they're about 15 degrees cooler than the surrounding landscape. And this is primarily what the remote sensing based estimates of evapotranspiration are based on is the thermal sensor from the Landsat satellites. It's not just the greenness of the fields, although greenness is taken into account in some of these as well. The Sentinel-Hub website makes it really easy to create these time-lapse animations of what the satellites are seeing. So here's from Sentinel-2, every 5 days, the true color and the Enhanced Vegetation Index. This data goes back to around, I think, 2017 or so. And it literally only takes 15 minutes to create these kind of animations, because these websites do all the processing for you. You just draw your area of interest. So this is, for those of you who don't have the valley floor of Scott Valley burned into your brain, that's what this is all the agricultural fields in the Scott Valley. So let's look at some comparisons between 2020 and 2022. So here's true color images for the Scott Valley and the Shasta Valley. These are all from exactly the same day, August 15th, but in the 2 different years. And it's kind of hard to see in the true color here. Pretty much impossible, really, unless you're looking at this screen here. But there are some areas that I've circled in the Shasta that were much less green in 2022 than they were in 2020. It's a lot easier when we look at the Enhanced Vegetation Index. Save my pointer. Yeah, so here's like an area here that was really green in 2020, and then is very little green there in 2022. When you look over in the Scott Valley, there's not such a dramatic shift between the 2 years. There is overall about the same amount of green. The fields have kind of like wiggled around a little bit, just depending on the cutting cycles of the alfalfa. Another way to look at this here, I'm going to kind of flip back and forth here between 2022 and 2020. So if you look at the Shasta, you see this really dramatic difference, right? Where 2022 is much less green than 2020. If you look at the Scott, you see, the green polygons are kind of wiggling around, but there's no major systematic difference between those 2 photos, except for the McKinney fire area here that burned about a couple weeks before these images. It looks like some of the areas that stayed green in the in the Shasta Valley were those that were groundwater sourced, and then in the surface water, some areas stayed green and some didn't. Here is the thermal band from the Landsat sensors, and you can see here that there's significant cooling of these irrigated lands in 2020, whereas if you look here, you don't see that same cooling, and there's more like uniformly hot in those areas. So again, that's a lot of what the satellite water use is looking at, these thermal bands from the Landsat satellite. So I wanted to give a little background information on what is consumptive use, what is evapotranspiration, and how does it relate to irrigation efficiency, and how does that affect water budgets at watershed scales. Found this great report from some ag extension agents up in the Northwest, and they're titled awesome. It says, the more you expose, the more you lose. So if you want to save water, you have to move the sprinklers as close to the ground as possible, decrease the pressure, increase the nozzle size, get bigger drops that fall straight to the ground and are not, swirled up into the wind and become, clouds hundreds of miles away. Here's an example of a mid-elevation sprinkler, or MISA. Here, it's a very fine mist. You can kind of see the rainbow there. It's released from a higher elevation, finer drops, and more likely to get wafted away by the wind. Here's a LISA, or a low elevation sprinkler. It's bigger drops at lower pressure, released right near the ground surface. And the difference between these two systems, I spent like a whole day reading, the current research papers on irrigation efficiency, and in some cases it can be, you can save 15 to 20% of the water by doing this switch. And this is one of the practices that is in that some of the ranches are implementing in their LCSs. I think that's a great practice. Another one is upgrades to the LIPA, which is essentially you put a sock on the end of the irrigation thing there, and the water is released right at the soil surface. So there's no spray, there's no drops, there's no wind loss. So it's a more efficient application method. This diagram here shows what can happen to water once it leaves the nozzle head of the sprinkler. I mentioned you can get the wind drift and the evaporation. You can also get water that is settling on the canopy surface of the crop, and that's going to increase the total amount of water that is used in that field, but it's not helping the crop grow. What helps the crop grow is water that gets into the soil, that comes up through the roots and goes out through the stomata and the leaves of the plant, and that's what drives growth in the plant. That's when you get crops growing. You get that's good thing for farmers, good thing to eat food, right? All these top three here is just purely wasted water. There's really almost no benefit that comes from that, and so that's what we should be focusing on in our irrigation efficiency, is things that reduce that wasted water component of the water budget. So that wasted water plus the agriculturally beneficial water, those two things together form consumptive use, or evapotranspiration. You can also get non-consumptive use of water, right? So if you're applying more water to a field than can be infiltrated into the ground, you get runoff, goes back into the stream, or you get deep percolation. And deep percolation is not the water is not lost or destroyed, right? It's groundwater recharge that then becomes stream flow later in the year. Those are non-consumptive uses. So if we're trying to increase in-stream flows at a basin scale, at a watershed scale, we need to focus on the consumptive use and reducing that. And if we can do that by minimizing the wasted water, that's great, because that's kind of a win-win circumstance, right? If you get into reducing the crop transpiration, then that's good for stream flow, but it's bad for farmers, right? But we may need to do some of that depending on what the goals are, right? So how do you measure evapotranspiration? There are specialized field measurements to do it. It's rarely done, or not commonly continuously, only in special places. You can calculate what's called reference evapotranspiration, or evaporative demand, abbreviated as ETO or ETR, and that's calculated from air temperature, wind speed, relative humidity, solar radiation. That gives you, how much water would a crop use, assuming it has access to all the water that it wants. And then every crop has a thing called a crop coefficient. It could be, a little higher than 1 or a little less than 1. You multiply those two together, and that will give you the evapotranspiration of the crop if it has everything it needs. You can also use remote sensing, which is what I'm going to talk about some here today. So here's estimates of the amount of water that is applied on a per area basis. So think of it sort of like precipitation, right? We know about okay, what is 30 inches of rain? It means every square foot or every square acre, that's how much water fell from the sky. So evapotranspiration would be the inverse of that, right? How much water is going from the land into the air. So in the initial Scott Valley groundwater model, they had calculated that alfalfa needs about 33 inches of water to be happy and healthy in the Scott Valley. They showed that to the groundwater advisory committee, and some of the ranchers said, no, we're not using nearly that much water. We're only using 21 inches. And they did a series of field studies, Steve Orloff and his colleagues, and measured, I think, about 3 or 4 ranches, and they confirmed that 21 number. And so then the groundwater model was revised to reduce the amount of applied water. Interestingly, when ranchers filed their LCS applications in 2022, they reported that they were applying 40 inches for their baseline and 23 inches for what they were proposing as a reduction. You can see that these numbers are not the same, and I think it's worth some evaluation of like what is the source and the methodologies, and which of these is the most accurate number, because they can't all be right. And only 5 of the 45 Scott groundwater LCSs reported baseline use of less than the 23 inches. That is currently what's assumed in the groundwater model. I'll present in a few minutes here the results from OpenET for average across this period that the evapotranspiration was about 31 inches. These are not exactly from the same geographies. There's differences in the field boundaries of the polygons and all that, but just wanted to point out that the major difference here is not discrepancies in how much water is being transpired. It's differences in how much water is being applied in irrigation. Okay, so going back to the Landsat skin temperatures and the remote sensing calculation of evapotranspiration. So OpenET is a collaborative project among many different universities, federal agencies, nonprofit organizations, private companies like Google. They use the satellite data, they calculate evapotranspiration 6 different ways, and then average it together to get the best estimate. It's calculated at a 30-meter pixel scale, then aggregated to fields. I wrote to them and they I said, here's my area of interest. Can you summarize the time series for all the fields in the Shasta and Scott? Actually, I had them do the whole Klamath Basin. And they wrote back and they, yeah, sure, we can do that. And they sent me back the data. So I'm going to present some summaries of that here. So I wanted to thank Will Carrara at OpenET for providing that data. Okay, so here's a totally oversimplified version of my understanding of how OpenET works, which is only a partial understanding, right? Okay, so you start with climate data or weather data, air temperature, wind speed, relative humidity, solar radiation. From that, you calculate the reference evapotranspiration, assuming a well-watered crop. Then they take the satellite data, mostly from that thermal sensor, and they calculate for every pixel what percent of reference ET is that pixel. You got to fill gaps when there's clouds and missing satellite data. So this is essentially sort of a dynamic crop coefficient that's changing in time and space, instead of just saying alfalfa is always a 0.9 or a 1.1 or whatever. You multiply those things together, and then for every pixel, you get the evapotranspiration of that pixel. And then it's rolled up to spatial scales. The measurement error on these things, compared to the fancy field measurements, is about 13% at a whole season scale, and about 16–17% at a monthly time scale. Okay, so here's some of the take-home results here. So I ran the watershed scale summaries for Scott, Shasta, as well as the Butte, which is a groundwater irrigated agriculture that's over the hill to the northeast of Shasta. And what you see, so here's monthly and here's annual. So in Butte and Scott, the consumptive water use was pretty flat from 2020 through 2022. In Shasta, we're seeing pretty substantial decreases, especially in 2022. And so I'm going to try to explain why that might be. Here's drilling into just the Shasta and Scott for just the last 3 years, just to make easier to digest data on a seasonal time series. So each year is a different color of line. So you see in Scott, they're all relatively close together, whereas in Shasta, the black line is 2020, so that was the highest. 2021 reached almost as high, the water use inches per month, but then it drops off sooner. And then in 2022, it really never reached anything close to the peak that it got to in the other years, and it dropped off sooner. If we look at the greenness of the fields, you see similar patterns as we see in the ET data. So I thought, well, could we compare the ET? Could we look at it on CFS units? And I'm just looking at the low flow time of here of July through September. So here is Shasta on top, and these are the y-axis is the same in the top panel here. So the maximum ET in 2020 is about 300 CFS in the Shasta. And interesting, if you look at the difference between 2020 and 2022, that difference in consumptive use, sorry, pointer's not working, but in the upper right panel, the difference between the consumptive use between the 2 years, interestingly, turns out to be pretty close to the difference in the flow between those 2 years. Similarly, in the Scott, there wasn't really a reduction in evapotranspiration between the years, and there wasn't a difference in the stream flow. Drilling more into the Scott here, that kind of teal green is the groundwater irrigated parcels or fields in the Scott. It's those groundwater areas that have the highest water use on a per area basis, and they're also the largest number of acres. So on a volumetric basis, that's where most of the water is used, is through the groundwater. And you don't see a reduction in the water or the transpiration between 2020 and 2022 for groundwater. Surface water use here actually went up a little bit, which I was pretty suspicious of that when I first saw that, and I'm not really sure what is going on with there, because surface water use was supposed to have been curtailed. Some of this could be sort of geographic mixings here, so I'm taking the field boundaries from OpenET and I'm overlaying those on the field boundaries from the Scott Valley groundwater model, and they don't line up exactly, so that could be part of it. I'm going to skip this one for now. Okay, so the local cooperative solutions in the Scott. So here's a map of all the LCSs in the Scott from 2022. I've numbered them from the largest to the smallest, just arbitrary labels there. So here's a plot of the estimated water use or consumptive water use for each ranch by their size. And so as you would expect, the larger the land area is of a ranch, the more consumptive water they're consuming. Most of the water use in the valley is, in the largest ranches, because that's where the land is, right? So just for the sake of legibility, let's zoom in on these top 20 or so ranches. So on the y-axis there is the depth of evapotranspiration, number of inches per year. So it's ranging from about 20 to about 36 inches per year. And they're all sorted by the black line, which is 2020. And so what you see is that there's some of these ranches that are using a little bit more water in 2020. Some are using some are using more in 2022. Some are using less in 2022. But on the whole, it's balancing out about not a major reduction. If we had seen a 30% reduction, this is what the line would look like. So clearly, it's not anywhere close to that, right? So in conclusion, I would say that the 2022 curtailments reduced the consumptive water use in the Shasta, but not in the Scott. But the LCSs in the Scott were not designed to reduce consumptive use. They were designed to reduce pumping from the aquifer. And so I'll ask the question, was that a good design? If we're trying to protect in-stream flows, we should probably target practices that reduce consumptive use if we're trying to increase in-stream flows at a watershed scale, right? The irrigation in the Shasta is mostly surface water, whereas the Scott is a mix, but with more groundwater. And so I wonder if at these watershed scales, is it easier to manage and control surface water than it is to manage and control groundwater, right? Everyone has their own well, so it's pretty hard to tell what people are doing, whereas if there's a ditch, you can see if there's water in it or not in it. Obviously, there's differences, as Eli talked about in his talk, about the geology of the two basins, and that's going to affect a lot, you know, how the flows snap back in the fall once irrigation ends. So I think there is a need for additional analysis and benefits from additional analysis. One would be to drill into this issue of like, well, how much water is actually being applied in the Scott, and do the studies that were conducted on those 3 or 4 ranches in the early 2010s. Is that representative of the basin-wide water use, or is what people submitted in their recent LCS reports, is that more accurate? And just looking at that issue more. Also, we don't have a field-specific GIS map of what LCS practices were applied to which fields. If we had that map, we could, you know, extract out the polygons of, hey, here's all the people who fallowed the corners of their field. Here's all the people who shut off their irrigation in August for those specific fields. And then we could run summaries and look at the evapotranspiration from the remote sensing. We'll see which practices reduced consumptive use and which didn't. For some of those, you could tell whether people did what they said they were going to do, right? If someone's not watering the corner of their field, that should be pretty obvious in August whether they've been irrigating or not, right? Other things like, were they running their sprinklers for 10 hours a day or 12 hours a day? I mean, there's really no way to verify that if there's no meters, and nobody has meters, right? This is just a slide of references from that irrigation efficiency research that I did. I just wanted to put that in the archive for people to look at later. And yeah, take questions. If I have time, I guess I don't. I'm at 27 minutes, so.
A lot to cover, Eli, a lot to cover.
I chose to go over everything really fast rather than anything individually. So yeah, we'll have to talk at lunch.
All right. Any real important questions? Dave, we'll pass the mic to you real quick, and then we probably should break.
There's a break after, so you can kind of talk to me then, yeah, too.
Yeah, Eli, I mean, this is dynamite stuff. What can we do to help you get this in front of the water board and regional water quality both?
I certainly would be happy to present this to anyone who is willing to listen to it. So yeah. And as far as help also, if someone could go through the 45 scanned PDF documents of the LCSs and map out the parcels of who's doing what, I could use that too.
All right, some GIS homework for someone.
Yeah.
Either online or in the room. Yeah, Crystal.
Did the ET rates vary according to water year type?
I would say yes. Well, I didn't formally look at that, but you probably know the years as good as anyone does. Let's see. I mean, you can definitely see they're bouncing around. Like 2017 and 2019 were relatively wet years, right? And the ET rates tended to be somewhat higher in those years. I think that probably has the biggest effect for surface irrigation, where like in the Scott, like the surface water rights for some of those run out in every single year, or the stream goes dry, right? And so in wetter years, you're going to be able to irrigate for longer. There's also just a little bit of the way the field boundaries are drawn to summarize in from OpenET. You know, some of those are like dry farmed parcels, and so when there's more spring rains or something like that, or more soil moisture, they'll stay green and use water longer into the summer. So there's definitely an effect of water year type, yeah. Probably not so much on the groundwater center pivot irrigation, you know.
Great. Eli, thank you so much.
Yeah.
That was great.